of the category required by in which the determinant take values. Let me make a simple remark about the paradox before I begin. So, my point is not to sort of give the generalization of main conjecture for previous projects and so on, but it's sort of more about for which groups, I mean, which kind of periodical extensions one can formulate the main conjecture. And so I'll always speak about the main conjecture in which main conjecture for totally real number fields. Okay, so whenever I give some example of the or formulation of the main conjecture, but for various kinds of groups. Okay, so let me recall what give a definition of what a Picard category is. Okay, so Picard category P it's a non-empty category in which all morphisms or isomorphisms, and there is a bifunctors, and there exists which plus from P cross P into P such that it satisfies various properties. So so the first one is so plus is associative. There's a bunch of technical conditions as usual in this kind of thing. So so i.e. there exists a natural isomorphism for any triplet. So x, y, z from x plus y plus, okay, I've written it in a different style here, so I'll just stick to my notes. And then the second one is this is commutative. I.e. again a natural isomorphism for any pair, right? Okay, so these in general may not be. So yeah, this is okay. Such that the psi x y composed with psi y x is equal to identity on y plus x. Okay, so these are the two things which satisfy what is called pentagon axiom. And then the second one is hexagon axiom. Since these are usually not written anywhere except in very few places, I'll write them down. So what does pentagon axiom mean? It's about how the associativity behaves, the associativity isomorphism behaves under various chain of things. So you have x plus y plus z plus t, and then you apply to this phi of x y z plus t this is just to make sure that if you have instead of 3, if you have many, then everything behaves nicely if you change the bracket. Identity on x plus phi of y z t. So this goes to x plus y plus z plus t, and this phi of x y plus z t, this should go to x plus y plus z plus t, then from this to x y z plus identity on t, x plus y plus z plus t, and then this one should be phi of x plus. So this commutes. Okay. So this is the pentagon action, and yeah, just because I promise I'll write down the hexagon, which is about how the two interact with each other, so that you can change the order and the brackets. X plus y, z, this goes to c plus x plus y x plus y plus z, and this goes to x plus z plus y. Okay, so this one commutes as well. Okay, and then the third condition is x going to x plus p and x going to p plus x are autoequivalences. on the category P. Okay, so this is just some definition of Picard category. Now coming to the main thing that we want to construct, so CR. That's, I'm giving a good example. Okay, so CR, Picard category of Fukaya and Kato. So this is, so objects of CR. So for any ring R, as before, as in the previous talk, objects of CR are pairs PQ, such that P and Q are objects of the PR from the previous talk. So they are finitely generated projective modules over R. Okay, and what are the morphisms? So morphisms are hard to describe. So morphisms of P prime Q prime is empty if P minus Q is not equal to P prime minus Q prime in K0 of R. Okay, so it's empty if they are not equal, but if P minus Q is equal to P prime minus Q prime, then so again in K0 of R, then there is then the morphisms is not empty, and it's given by the following. So if this is so, then you can just, this means that P direct sum Q prime is P prime direct sum Q. And what does it mean for two elements to be same in K0 of R? There exists a finitely generated projective R module, say S, such that P direct sum Q direct sum P Q prime is isomorphic to P prime direct sum Q direct sum S. Okay. So what I do is I put GS to be the group of automorphisms. So R automorphisms of the target. So P prime direct sum Q direct sum S. And then you put I of S to be isomorphisms from P direct sum Q prime direct sum S into P prime direct sum Q direct sum S. Okay, finally we can define what morphisms are. So K1 of R cross, so you take the product between K1 and IS and mod it out by action of GS. So this is K1 so how does GS act on this product? So G of X and Y is given by X G bar inverse G of Y. So automorphisms of the second thing act on that by, you just compose Y with G. So this is just composition, and G bar is just the class of P direct sum P prime direct sum Q direct sum S and G living in K1 of R, okay, by the definition of K1 of R. And I'm just taking its inverse and multiplying it with X. So this is the action. So morphisms of PQ and P prime Q prime is a K1R torsor. So it's a set on which K1 of R acts freely and transitively. Okay, the group K1 of R. Okay, so so I've told you what the objects are. I've told you what the morphisms are. Now it's kind of, and then so there are few things that we have to check. First we have to check is independence of S. So we have chosen S, and so we have to show that the morphisms, the definition of morphisms doesn't depend on S. So if S prime is such that P direct sum Q prime direct sum S prime is isomorphic to P prime direct sum Q direct sum S prime, then put T equals S direct sum S prime. And so the same is true for G of T, and then what we will show is that K1 of R cross GT IT is isomorphic to K1 of R cross GS IS. Okay, and what's the map? So an element represented by X and Y will go to X and Y direct sum identity on
S prime. Okay, so this is an isomorphism. If we show this, then we are done, and this is quite easy to check.
So Mahesh, this is introduced in the Fukai-Kato paper.
Yes. Okay, so where are we? So we have to show that every element on the left hand side of that map can be represented by x comma some element in k1 comma something times identity on S prime, and that's easy to do. So you just take x and y in k1 of r cross I of t. So y is an isomorphism from p direct sum q prime direct sum s into p prime direct sum q direct sum s prime, and then you just look at the image of S prime. Okay, so say something like image of y restricted to S prime. This goes to prime direct sum q direct okay, so and you get something like this. Now what you do is image of y restricted to S prime is isomorphic to S prime, and so you take that so this is, I mean, this is some isomorphism I, so you get image of y prime, and then now you don't take this thing but with the isomorphism, and so it lies in S prime, and that gives you p direct sum q direct sum S prime. Okay, and so you can so this is projective, so you can split it, and so you get something like okay, and you okay, so this is the element in this is the isomorphism in G of t that you that you take on this, so you get y goes to something like y prime direct sum identity on S prime, and so everything is in the image, and then by doing the same process you can show that it's injective because you can define the inverse. Okay, so this is independence of the choice of this thing. So, and then the second thing, I have to tell you what the composition is, and again this is some lengthy arrows, and I think that's why it's not given in the paper. And, okay, so you want morphisms p q to p prime q prime to so let's say there's some, I mean the s there is s here, and then I have some s prime here. So what do I have to do? You have to take p direction q double prime to get a morphism here, and then what I do is I just take q prime direct some s prime, and I switch around the thing. So I write any kind of switching isomorphism will be written by s. So I switch around things and I get p direct some q prime direct some s direct some q double prime direct some s prime, and then I use the morphism here. So okay, so I have to compose x, y and AB. So I just use the B here, B direct some identity on this thing to get P prime direct some Q direct some with S direct some Q double prime some S prime. This again I use the switching to go to P prime direct some Q double prime direct some S prime direct some Q direct some S, and then I use the Y here to go from the first three things here to P double prime direct some Q prime direct some S prime direct some Q direct some S prime, and then I switch again. So I get P double prime direct some Q direct some, then I just have those things here. So I write the whole thing as C, and so I define x comma y composed with a comma b as x times a times q prime minus 1. So this is the class of the automorphism on q prime given by minus 1, and then this is C. So I take the class of this in in the morphisms like this. Okay. So this is the thing that you have to be careful about, because you are switching thrice. So if you don't put this one here, you somehow get minus 1 where you should get 1. Okay. So this is the composition. Okay. Now what is the use of this functor?
So is this notion due to them, or was it, did Picard really have anything to do with Picard categories?
Line bundles.
Yeah.
If you can do, if you forget about the zero-morphism between line bundles.
Invertible morphism. The link of this picture.
Yeah, I think a better example would have been to take a local ring and then the invertible modules over that ring, and then sort of make it into a category.
Somehow the idea is that determinant of modules even over non-commutative rings are supposed to fit in this module, even if it's not an invertible module. That motivates.
Okay, then one can check all these. Okay, I should tell you what these P's and C's are. I won't check all these horrible diagrams commute. It's not sort of difficult. So again, one has to be slightly careful about. So how does one define the pi functor on this? in the definition I used plus, but I'll use multiplicative notation here because we are in K1 and I use multiplicative notation for K1. So this is what we want, and then psi p q to p prime q prime. So this should go from p direct sum p prime q direct sum q prime to p prime direct sum p q prime direct sum q, and again you just have to be careful about the switching here. So this thing is equal to the class given by q direct sum, the q prime direct sum q and minus 1, not that it makes difference, but and then the switching isomorphism on this side. Okay, so this is the one, the commutative isomorphism, and this thing is just identity. Okay, so this makes, all this thing makes CR into a Picard category. So what's the use of this thing? The use is that we have a nice functor from the category of finitely generated projective modules into this, which behaves like the determinant functor in the commutative case. Okay, so one comment about this. So if we have a nice commutative ring R, then we can think of PQ as the highest exterior power of P, and then the inverse of the highest exterior power of Q. And that's the way it works. So this is where determinants should live. Okay. Okay, so there is a functor which I denote by determinant R from the category of finitely generated projective modules over R, but now I just take those those morphisms which are isomorphisms into CR given by determinant R of P is P comma 0. So the comment is that this is a determinant functor in the sense of Deligne, which means that for all short exact sequences sigma, which are like so I'm using a short exact sequence instead of the direct sum here because the order will matter, and I'll come to that in a second. There exists an isomorphism between determinant R of P and determinant R P prime. P double prime. Okay, so this is a functorial isomorphism. meaning that if you have two short exact sequences and maps between them so that they commute, then this isomorphism commutes with the natural map that we obtain. 2 is that the 0 goes to 0 of the Picard category. Sorry, so I should have said that if this autoequivalences gives that there is an identity in the Picard category. Of course, it's not unique, but there is an identity. So what's the identity in this? So the identity in this is 0, 0, and it's not unique because P comma P is also an identity for any P in this category CR. Okay, but 0 goes to 0, that's also clear. And isomorphism gives you elements, but then one has to be careful about so this is an so this third thing has to do with the choice of convention, I guess. So one can look at this as a short exact sequence in two ways. So you can look at it as 0 goes to 0 goes to P goes to Q goes to 0, and we choose this to be the image of phi in here is this isomorphism, which is between P so determinant R of phi. So this is between determinant R of P to determinant R Q, determinant R 0 to determinant Q. But then there is of course there is another way to look at this isomorphism, which is 0 goes to P goes to Q. So this is another short exact sequence, and this is defined to be phi determinant of phi inverse. And this goes from determinant of Q to determinant of P. Okay. And then lastly, if P is contained in Q is contained in S, and these are admissible, I'll talk about this more next time, but what this means is that quotient of S by Q and S by P and Q by P are all projective, so this need not be true in general. So we can talk about their quotients in our category, and then this thing so this is all clear. So this is P into determinant R S of P, determinant R P, determinant R of Q mod P, determinant R S mod Q. Q, this commutes. Okay. So what does this mean? This means, so Deligne calls any functor from this P, so any functor from PR into isomorphism to some Picard category P would be called a determinant functor if it satisfies these 4 conditions.
S mod 2 in the lower left hand.
Yeah, S mod. Okay. So any functor like this which satisfies the properties, these properties will be called a determinant functor. And then, in fact, as
Kind of a uniqueness statement of some kind?
no, I mean I haven't said anything about sort of. So there is a uniqueness. Okay, so that's what I'm coming to. So for the CR, there is some kind of uniqueness statement. So okay, but then we have this determinant functors into various Picard categories, and so this P R into CR is the universal is okay. The universal determinant functor is the universal determinant functor of Deligne. So what Deligne does is he constructed a universal determinant functor, which means that i.e. if f from PR isomorphism into P is a determinant functor, then there exists this thing which commutes. It's sort of unique up to a non-unique isomorphism. So okay. So so how does the I've not told you what the construction of Deligne is, but I think that will be the part of next talk when I talk about K-theory spaces and so on. So Deligne constructs the category of virtual objects. So let me call it V, P, R, and then there is a natural functor from this into isomorphism into this V, P, R, and this is the universal, and he shows that this is the universal determinant functor. So our determinant functor will, so this will factor through the determinant functor that we have constructed, and then Deligne proves that if the group of if the group of objects which are isomorphic in these two category, that's the same. So meaning that K0 of VPR is equal to this, and K1 of VPR is equal to K1 of CR, which by definition is automorphism group of 0. So this in both the things, because this condition holds, this should be an equivalence of categories. So if for any Picard category these two conditions hold, then it should be an equivalence of category. And this the way we will construct this next time, this will be K0 of R and K1 of R. So it has to be the universal determinant functor. Okay. So what do we use this for? The universal determinant functor. So if I call C, I don't know, any notations, maybe something like category of perfect complexes of R modules. So the category of the category of bounded complexes of finitely generated projective R modules. Then one can extend the determinant functor to this category by just sending any complex to C even, C odd, where C even is C R even, and C odd is directs an R odd C R. Okay, that's a finite sum. So this is the determinant functor that we are interested in. Okay, so let me write down some properties of this which we want. And then at the end I'll state a general Iwasawa main conjecture for totally real fields. So these are all very clear. So for instance, determinant of CR is naturally isomorphic to determinant over R of C minus 1 to the R. So okay, just by looking at the definition. So here CR by C, or I mean, so the pth thing in this is C R plus P, and then the differentials maps are also changed by plus or minus 1 depending on the degree. Okay. 2 is if there is a short exact sequence then there is a match. So this is all by the properties of the determinant functor. So determinant of C times determinant C double prime. So this third one is that we will use. So if C is acyclic, then determinant R of C is canonically isomorphic to determinant of 0. Okay, and so on. So let's see. The fourth thing is determinant R of C is isomorphic to determinant R of 0 if the class of C in K0, which is by definition the class of C even minus C odd, is 0 in K0 of R. So this is clear from the way this category CR is defined. So let me give a general formulation of main conjecture. So
Say that this is the thing is a K1 torser?
sorry.
You said something about it being a K1 torser.
Yeah. So what's morphisms between any two objects is a K1 torsor. This is a K1 torsor. So just as sort of what you would expect. So
Space of determinants is not a K1 torser?
Morphism.
The morphisms between two. So I don't know. So the space where the determinant functor takes values is this category CR, and the morphisms in this category is a K1 torsor. So that means that if you have any isomorphism, so let's say you have an isomorphism between two finitely generated projective modules, then this is to say that this isomorphisms gives you an element in this K1 torsor. And now if you look at morphisms between PQ and PQ, then this will be actually K1. This is automorphisms of PQ to PQ, so there is a distinguished element identity, and so you can make it a K1 group. And so if you have an automorphism, then this will give you an actual element in K1. Okay. Yeah. So for instance, this. So if C is acyclic, then I can look at automorphisms of determinant of C, and because this is I can look at isomorphisms between C and determinant of 0, and this will in general be a K1 torsor, but in this case, because they are canonically isomorphic, I can turn this into a group which is isomorphic to K1, and that's what's sort of used in the formulation of the main conjecture. So
maybe I'll just make one
Yeah.
comment. I mean, Mahesh is going to do this later, but for the sake of intuition, it's useful to know that there's actually an underlying space where K0 is pi naught and K1 is pi 1. So that in fact, if you take two different objects, but the morphisms are actually paths from one point to another. So the determinants are points inside this space, and morphisms are paths. So that's why it's a K1 torsor. It's a path for pi, torsors for pi 1.
So in fact
These
that
spaces of what?
These are for K-theory spaces.
Okay.
so in fact for this so this PR is an exact category, and so Quillen constructed this K-theory spaces for exact categories, and the way Deligne constructs these virtual objects is, so by definition his objects in the categories are points in this K-theory spaces, and no, sorry, there is just one, sorry, there is a zero object, and by definition the objects in the virtual category are loops at these based at the zero object, and the morphisms are homotopy classes of homotopies between two loops.
If you mention that, that makes it confusing again.
Yeah, sorry, yeah, that makes it, right. I mean,
K-theory space is actually, the K-theory space is a loop space of something else again.
yeah, sorry, yeah, sorry, yeah, that makes it confusing.
That's not to mention.
Okay, so this is, so the generalization in this sense is done by many people, but the way I state it here is sort of using the exact sort of statements given in Fukaya and Kato, and so I just write their name.
Other three authors are
Yeah, but I'm not using this or set S and so on. So
but it informs this formulation.
yes, so yeah.
No, they were first.
This was before your.
Yeah, of course.
Oh, I didn't know that.
I mean, this is somehow the formulation is already in this Kato's 93 paper, the lectures on.
This formulation? Oh, yeah, I guess.
I mean, yeah, but just for commutative R, so he didn't use this. But essentially, I mean, this is the setup that he has. If he uses virtual objects, then this is exactly what he gets. But he just used Mumford and Knudsen, so.
Never read the 93.
Okay, so so again I'll do just over Q, and I can take any totally real field, but and this contains Q mu P infinity plus. So as I said, I mean I'm interested in taking arbitrary groups here, so I'm not sort of doing it for arbitrary totally real fields. This and then, so what assumptions do I have on this extension? So I assume that only finitely many rational primes simplify in F infinity. F infinity is totally real Galois over Q. I denote G by Galois group of F infinity over Q, and I assume that this is a p-adic Lie group. Okay. And now I have the complex as before. So this is R home. One-trigon dual of the following iterative homology. So sigma is a finite set of primes of Q which contain all those which ramify in F infinity.
So in this case, this becomes the same as the Selmer complex?
This is the Selmer complex.
You don't need the F condition.
The F condition meaning?
I mean, in general, if you have
Oh, yeah,
you need to modify this using a cone of some map or local stuff. You don't need any of that.
No, so somehow, I mean, in this condition, in this case, the F conditions are that it's unramified, and because I'm inverting sigma here, so I'm just the local conditions are unramified outside P.
Yeah, but the condition at P is also automatically taken care of.
Yeah, right. Because somehow.
Everything is in F.
Yeah. Okay, so for this module, okay, so now, okay, yeah, that's okay. So what? So proposition. So this is sort of again in Fukaya and Kato, but a proposition like this was proven in a slightly weaker case by Flach. And so this says that the class of this is 0 in K0 of lambda G. Okay. So this implies that there exists an isomorphism between determinant lambda G 0 and determinant of
So what goes into the proof of this proposition?
the proof this that when you reduce this to finite levels and so on, you get the Euler characteristic is trivial, something like that.
But I mean, do you introduce to one of Iwasawa's superatomic theorems?
No, you reduce it to the finite
Yeah.
case, and then use State's theorem.
Euler characteristic
Yeah.
Yeah.
I see. So there's nothing about knowing modules of torsion.
No, this is not a statement about torsion, I think.
Mhm.
Okay, so and what does the main conjecture say? Main conjecture says that there is a special isomorphism which Kato calls the zeta element. So there exists an isomorphism zeta from determinant 0 to determinant so I just twisted by something for correct normalization such that for any artin character rho from G to GLM O. So O is some finite extension of ZP, ring of integers in a finite extension of QP, and any even integer greater than 0. So recall kappa was the cyclotomic character. So we have rho kappa to the R from G to GLNO. So this gives us a map from rho kappa to the R from lambda G into Mn of O. Yeah, this is slightly. So the torsion conditions they'll come somewhere here, I think. Okay, so I just put L here, and okay, so this is a ring homomorphism, and I can take any. So this ring homomorphism gives me a map into C of M and L. So how does this map go? This goes from Q into P. So I guess I'm looking at everything as left modules. So L to the n tensor lambda G. Okay. So using this thing, this isomorphism will be sent to an isomorphism between determinant over mn L into determinant over mn L into Ln tensor with C, and then sort of conjecturally this thing is acyclic. So that's where the torsion conjecture comes in. So that's sort of I mean, as usual in Iwasawa theory, you have sort of two conjectures. That one is about the torsion thing, and then you can sort of start doing Iwasawa theory. So then Ln C is acyclic, and the composition of so did I give name to this? I should give a name. Let's say zeta rho kappa to the r. Imposed with the canonical morphism. So can is from determinant MNL of C to determinant of 0. So this is an automorphism between determinant of, this lies in the automorphism group of determinant of 0. But determinant over the ring M and L is same as determinant over L. So this is what one may call Morita equivalence. Okay, so this belongs to rho kappa to the R composed with belongs to L cross. And then the main conjecture says then this thing, then zeta rho kappa should be this non-zero L value. So you remove Euler characters at sigma and you get 1 minus R rho.
Okay, so in this case, this even twist corresponds to a non-zero L value,
Yeah.
and that corresponds to localizing already somehow.
Yeah.
That's where that comes from.
Mm-hmm.
And R here is even. Right?
Yeah, R is even integer greater than 0. So it's a critical value. Of course, they make it in much more general situation for various motives and non-critical values as well, but at a finite level, not at the infinite level. But this is just to sort of give a flavor of what the generalization looks like.
So sigma contains, of course it does contain surprise about.
Yeah.
What did you say about finite level versus?
Oh, so what I mean is that you take this extension to be finite, and then they make this conjecture for various motives even at non-critical values.
This is this equivariant.
This is the equivariant Tamagawa number conjecture. So, but because they can make this thing, the main conjecture in this language, they can prove that the equivariant Tamagawa number conjecture at various finite level implies the main conjecture.
But do they need the non-critical conjecture at all the finite levels?
No, they don't need it for the main conjecture. It's just that you can make it. Of course, to prove Huber and Kings, they in their ICM talk they have this strategy for proving the equivariant main conjecture, and what they sort of say is that you take the big extension which trivializes the motive, and then look at the main conjecture for that. But then I don't really understand how to go to the non-critical values from the big main conjecture. But yeah, even the strategy, the sort of systematic strategies for proving equivariant main conjectures is through Iwasawa kind of main conjectures.
But roughly speaking, non-critical values involve some denominator. For the p-adic.
Well, no, you don't have any L value. I mean, it's a
yeah,
leading curve. Well, it's a leading
It's the leading
curve.
Yeah.
So let me point that out. So what's happening here? So how do we get from the zeta element to the p-adic L function? So the zeta element is an So zeta element is an isomorphism between these two things, and this is of course not acyclic. So this lives in some K1 torsor.
Right.
Now, to get an actual p-adic L function in the classical sense, what you need to do is you take some. So then sort of you need to make the conjecture that this is a torsion lambda g module, or even better, you define some OR set, and then it's a torsion module by that OR set. And then you change the rings as we went from this to this. You can go from lambda g to its localization, and that would give you an actual element in K1 of the localization.
Right.
And so that will introduce the denominators. I don't know if that's you are meaning denominators in that sense.
We can discuss it then.
Okay.